Welcome back, everyone. So in this episode, what we want to do is take a look at calculating some experimental error with a hydrate. So if you haven't watched the previous video where I use this exact example, and from this example the focus was to figure out with the 7.5 gram sample that we're starting with exactly what the formula is. So you'll notice here that there's an X in front of the water in the hydrate formula, because the whole purpose of this problem in the previous video was to figure out what's the molar ratio of water to anhydrous salt, and we figured that out. So if you haven't watched that one, you should stop this video now, go to that one. I'll have a link in the description below that will help that you can get to that, or you can just go to the channel page and click on the video list and it'll be there. So alright, if you're still here, I'm going to assume you've already watched that video and you're ready to proceed, or you think you understand that. So let's get started. How to get that one last sip of that coffee before we get started. Okay, so right here, that data right there, this was the mass of the dish plus the salt, right? And we had figured out that 4.01 grams of salt is what we still had, and then what we had in the dish after the 3 heatings, right? And then we had 3.49 grams of water that had evolved off from the reaction due to the heating process, right? And so we did all the work on that, we did the math, blah 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 blah, we figured it out, and we saw that we had a multiplier of 6, and so we calculated and determined that this was a hexahydrate, right? Cobalt 2 chloride hexahydrate. So to get percent error, remember percentage is a portion, it's a fraction, and so we need to know what percentage or portion or fraction is the salt, and what percentage and fraction of the fraction is the water molecule. So if you think about it, I don't care what the sample size is, it doesn't matter. Regardless of the sample size, the question is how much mass can you expect every single time, whether or not your sample size is this big or that big. It really doesn't matter, because this formula here says for every 1 mole of cobalt 2 chloride there will be 6 moles of water, and that is a fixed ratio. It's never going to change, which means if that's a fixed ratio, that means the percentage by mass will always be the same, whether or not the sample size is this small or that big. So that's kind of what we need to figure out. So we've got to kind of go back into some Chem 1 skills, some basic mass percentage skills for Chem 1, right? So we essentially need, if you think about it, the molar mass for this. We need to know what's the mass of this formula. Let's just pretend that we were picked this up and we were holding X amount of it. We were just holding, well, let's just say one of these. We were holding one example of these where there's 1 cobalt 2 chloride and 6 water molecules that are bonded to that one. Let's just pretend there's that one. All right, because if you take moles and reduce it down to the smallest ratio, we're looking at individual molecules, right? So let's just pretend we have 1 molecule of cobalt 2 chloride surrounded by 6 molecules of water. If that were the case, that brings us back to basic Chem 1 type stuff, right? And so we have to know what the mass of cobalt is. That was pretty bad. What the mass of cobalt is, and the chlorine. Well, we see there's 1 cobalt and there's 2 chlorines, right? And so we go back And cobalt 58.93. So we'll use 58.93. It still gives the same thing. And then cobalt chloride. So chloride 35.45. So let's go back to our whiteboard, right? So right here, this was 58.93. Now, I could write AMUs. Typically, we know the units are going to basically cancel themselves out. We essentially want to know molar mass for all of this, right? We know we're dealing with that. So so that we're in the good habit, let's just put AMUs. And then this is 35.45 AMUs, right? So of course this is obviously 58.93 AMU, and then we have 35.45 times 2, that is 70.90. Alright, add that all up, plus 58.93, and we get the 129.83 just like we did in the previous video. Now in the previous video we figured this out kind of off screen, but since the purpose of this video is for us to see the entire process on how we're thinking through this, I figured it was important to show you all this. You can add like units, so there we go, AMU. Okay. And then let's come over here. Water, 16 for oxygen, 1.01 for hydrogen. There's 2 of those, that's 2.02. So that's basically 18.02 AMU, but we've got 6 of those, right? So if we've got 18.02 times 6, that gives us 108.12. All right, that gives us 108.12, and then that is AMU. So the total mass, right? So of the hydrate would equal the 129.83 AMU plus the 108.12 AMU, right? And so it's plus 109.83, 237.95. All right, check my math for me. We all have seen that, like I can rush this, and I tend to make some mistakes, but I'm pretty sure I'm right on this one. Yep, I included the 9 this time. All right, so now let's think about this for a second. We've got 129.83 out of the 237 is the cobalt 2 chloride. We have 108.12 out of the 237.95 that is water. Those are 2 ratios that we can basically get a fraction from, which will give us a percentage. And obviously those percentages would have to add up to 100% because both of the numbers together add up to the total mass, right? All right, so we can look at this and think that percent mass of the cobalt chloride, right? Let's think about this. So cobalt chloride, it's 129.83. That's AMU divided by the 237.95 AMU. Those units are gone. Remember, it's about the units. And then, of course, to get a percentage, you always have to multiply by 100. You always do. All right, so let's figure that out. So we've got 129.83 divided by 237.95 times 100. You should get 54.5618827. There's a whole bunch there. So we just need some extra numbers. All right, we just need some extra numbers. So, we're looking at probably going to the hundredths place. We went to the hundredths place with our our molecular weights off of the periodic table, so that's probably a good place to stop right there. Always put an extra number and then evaluate it down to a number that seems to make sense rounded properly, so we can evaluate that to 54.56%. All right, so now we need percent mass of the water. And we figured out over here that the water was 108.12 AMUs. And that was out of our total, which is 237.95 AMU, units gone, times 100. I know I say it a lot, but it's just, I can't overemphasize it. It's about the units. In class, constantly, for years, and it's the same mistake over and over again. Even the brightest people will say, call me over, Tib, is this right? I'm like, I don't know, is it? And if you would follow the units and you see the units cancel out, you can trust your answer. Okay. So we got 108.12 divided by 237.95 times 100. We should get 45.438, and we can probably stop right there. We can see that hundreds placed there, that 8 would round that up to 45.44%. And if you add both those numbers up, there's your 100%. So what does this tell us? Okay, let's think about this. No matter what the sample size is, because the ratio of salt to water is 1 to 6 in this example here, for every 1 cobalt 2 chloride, there are 6 water molecules, then that means that it'll always, that no matter what the mass of your sample is, 54.56% of it will always be the salt part, and 45.44% of it will always be the water part. So I mean, it's close to a 50-50, but that there's enough of a difference there, right? So armed with this knowledge, we can go into any sample size and we can figure out theoretically, if we had no error, how much should be salt and how much should be water. So let's think about this. We had up here 7.50 grams. Okay, so we have a 7.50 gram sample of cobalt 2 hexahydrate. All right, so the mass of anhydrous salt, you could also say the anhydrate, that would be the same thing, right? Would equal, let's see, I'm going to even be more specific, put comma, and put COCl2 so we know specifically what it is. So let's think about it. We've got 7.50 grams. We have to multiply by the percentage because the ratio never changes. So we've got to multiply by 54.56%. All right, so now that's 7.50 grams times 0.5456. Let's punch that into our calculator here. See what we get. 7.5 times 0.5456. You should get 4.092. So 4.092 grams. And we can go ahead and evaluate this to 4.09 grams. Since we were working with 7.50, 3 significant digits, and we're in the hundredth place, then the 4.09 will work. If we had a more sensitive scale, we could go out to that third decimal place. All right. Now let's figure out the mass of water. Okay. Mass of water, so again, that was, the sample is 7.50 grams times the percentage of water, 45.44, times 45.44%. So that would be 7.50 grams times 0.4544. Okay. 7.5 times 0.4544, 3.408. So that gives us 3.408 grams. We can evaluate that to 3.41 grams. So all of this here, all right? So all of this here is our theoretical. All of this is our theoretical yield. That's what this is and this is, okay? Our experimental yields, let's think about this. Our experimental yields, if we go back, our experimental yield we had figured out in the previous problem for salt was 4.01 grams of salt. Was 4.01 grams of salt. Can y'all hear that thunder out there? There's some crazy storms going on. I mean, it's cool to listen to. Hopefully, it's not interrupting our video too badly. All right, that was our that was our experimental yield. All right, this was our experimental yield, which is the same as like your actual, right? Okay, so I don't want you to confuse that with expected, all right? Because that's what the theoretical is. So our actual yield was this. And then we actually had 3.49 grams of water. All right, so you can see here that the numbers, I mean, they're very, very similar. I'm assuming if you're here, you've already watched the other video. We evaluated two things in the last video. That we had an integer value that was close to 6, but it was higher than 6 than we thought. I mean, we had almost a third of a mole in there. It was like 0.27, right? It was 6.27. So we really should get a number that should have been closer to 6, right? Well, we had said two things. That 6 probably was the multiplier that we could correctly identify, and it was. And, however, looking at this right here, using the 6, okay, using the 6, what we've done is we've figured out these percentages here. Using the 6, we have figured out the percentage of salt and the percentage of water. And notice that our theoretical for the salt is really close to what we made, and the theoretical for our water is really close to what we made. So there's more confirmation that we guessed correctly, that we evaluated correctly, that 6 to 1 was our molar ratio in the previous video. So we were correct on that. But now this becomes a basic Chem 1 problem where you just use the percent error to figure out how much error do you have in this, right? So remember that percent error, and the percent error is the same for all the reactions. So, but let's do this one at a time. Percent error of the cobalt to chloride yield. Remember, mark everything you're doing. Be specific. Remember, so you've always got your actual minus your expected absolute value, right? Divided by the expected. And then that's always times 100. So the actual, we have 4.01 minus 4.09. So we've got 4.01 grams minus 4.09 grams absolute value, because there's no negative percentage here. There's not a negative amount of mass, right? And then we again had expected 4.09 grams times 100. You should see that if you take the difference of these two right here, that you would get 0.08 grams over 4.09 grams times 100, and you should see that the grams unit goes away. All right, so let's see what we've got here. Let's see. divided by 4.09 times 100, we can see that that gives us 1.9559%. So we're approximately at 1.96%. Okay, that's the error for our salt. It's pretty good. It's pretty low. All right. So, but that little bit of error contributed to us being that much higher than our value of 6. If we were closer to the 4.09, we would have had less error, and so the mole ratio would have gotten closer to that 6. All right. So now one more bit. Percent error of water yield, again, is actual minus expected over expected. And of course these are yields, right? So, all right, so our actual yield of water was 3.49. Okay, in the previous video it was 3.49. So the actual was 3.49 grams, and theoretically we've calculated up here 3.41 grams. And you should notice you really can't make more water than you're supposed to, but remember it works in both sides. We've already talked about how error can be the same amount, magnitude, one way or the other, positively or negatively, so to speak. Right? And so again, that's divided by 3.41 grams, right, times 100. Right? Remember, we expect to get 31, even though we actually got 3.49. What you expect represents the 100% of everything, right? So you should see that, again, there's a difference of the 0.08 grams divided by 3.41 grams times 100. Once again, that unit's gone. Right? 3.49 minus 3.41. 0.08, I don't know why I just did it in the calculator, divided by 3.41 times 100. Check my math, but you should have 2.3460%. So we're going to go with 2.35%. So there's our answers. Percent error for the salt that was in this lab that was when this hydrate was decomposed. The error that we have in what we should get is 1.96%, and the amount of water error that we have that we produce with water vapor, 2.35%. Relatively low percentages, but high enough to be significant enough to change our multiplier from from closer to 6 to 6.27. Okay, it's just significant enough to alter that value. All right. Hopefully that helped. I'm gonna finish this cup of coffee and just move on to making some other video. Hope this helped. Take care. You have a good night.